In this lecture, I'm going to talk about mass spring damper system dynamics and about lab study on vibration modeling and the use of accelerometers for vibration measurement. Accelerometers and their use and selection will be discussed in a separate lecture. But in this first week of lab, we're going to focus on just a single degree of freedom system, which is a single mass suspended by a spring damper configuration. So consider like this single story from a two-story building model, which we'll actually study in the second week of this lab. On this system, we put an accelerometer on that moving mass to measure acceleration. We give it an initial condition because the mass is displaced, and we study the unforced response. This lab setup uses a flex guide design, so we get essentially this level lateral motion, as you can see. So we're going to be focusing mostly on unforced response in this lab. Again, only giving initial conditions, but note that the accelerometer, which we'll see is also a mass spring damper system, works by forced response of its base. And we'll talk a little bit more about that in the accelerometer lecture. A follow-up lab will introduce an additional degree of freedom by studying a two-story building model, so we can see what it takes to model and analyze systems with multiple degrees of freedom. Now what I'm going to do in this lecture is first, I'm going to review two common mass spring damper system models that we can use to analyze practical systems, and I'll show you some examples. Then I'm going to show you how this model can be put in a standard second order ODE form. And that's very helpful because it helps us to identify the parameters referred to as natural frequency and damping ratio, which you may have seen in other contexts. I'll also show you then how these models can be applied to some practical vibration problems, review the models the physical models, if you like, that we put together in the lab, and then typical lab objectives for this, for say a first week of lab, and then talk about methods that can be helpful in improving your estimates of system parameters such as mass damping and of course natural frequency. I'm also going to show you how to use log-decrement method for measuring the damping ratio directly, and in doing that I'll show you some simple lab UVIs that you can put together for that and also use in the lab. So what I'm showing here are two different configurations that are helpful to think about in the context of this couple of labs that we're going to have here. One we can call a fixed base configuration, which is the most common one that you're probably used to seeing in different classes. You have a fixed base here, and note I'm showing the constitutive laws. Like for this spring, if we assume that it's linear, the stiffness relates the force on the spring to the displacement of the spring, and also a damping parameter, B, relates the force on the damper to the velocity of that damper, which is the relative motion of the two ends. And then we have momentum, linear translational momentum related to the velocity of that mass. So this is a very common mass spring damper system that you've seen in many contexts, and again, very useful in modeling basic structures and so on. The other is a base excited configuration, and this is a little different. In this case, well, coming back here to the fixed base configuration, I'm showing that there's a force applied here, and that might be something of interest, right? We want to know how this system might respond to different forces that are placed on here. In this case, when you have base excitation, while you could have a force on the mass, and of course you could have gravity acting on the mass, what's happening now is that the base is excited, so that's a little bit of a different configuration, right? As opposed to the a fixed base. This is a model that you might use for, say, modeling the vehicle suspension. The base here, you would have a model of that moving over the ground. Also, most seismic sensors, which an accelerometer is one class of, this is a model for different types of seismic sensors, whether they're made for measuring velocity or acceleration, which is the case for accelerometers. Again, whenever you'll see the values K and B given as here, we're making the assumption that those elements are modeling um, materials or components that have linear constitutive relationships between the forces and their respective parameters, in this case velocity or displacement. Okay, and that's something that you will have seen in your dynamic systems class, for example. Another thing I want to point out again is that those models can be used not just for translation, but also for a lot of different cases in rotation as well. So, and then also by understanding how, and I'll show you shortly, you can formulate those equations into second order form. What we're going to be talking about applies to any physical system that can be modeled with a linear second order differential equation. But the key thing also is just to be mindful of the fact that in some of these cases we're going to be looking at forcing. So you might have forcing, as I said, on the mass or at the base, and typically we'll have force applied or velocity applied. Typically we'll only have those two. Sometimes we're only interested in unforced response, and actually for probably for both weeks of this experiment on vibration, we're going to actually be looking at unforced response. What that means is that we're not going to have any applied forces, and we may not even have any applied base motion. What we're going to do is apply initial conditions to the system and release it and watch the unforced response, and that's sufficient for us to test our model. Okay. In other cases, we might be interested in forced response. And in those cases, we might have step inputs, impulse, or sometimes, harmonic input, like in a vibrational system. And in fact, as I mentioned before, the accelerometer itself, being a base-excited system, is actually under forced response. And I'll talk a little bit about that in the short lecture that I'll give about accelerometers, but probably won't go into forced response in as much detail in these two labs as you might see in your 344 or your dynamic systems lecture course. So let me go over a couple of examples just to show you how those models are used. Again, this should be familiar to you, but say you had a system like this. This shows like an unbalanced fan sitting on some kind of structural support. Let's say this is a compliant system that also has some inherent damping in the material. And this is showing that there might be an imbalance rather in the impeller. And what would happen here is that you'd get, and I'm showing that over here, a mass that would be rotating about this axis that would tend to cause some forcing. So something that you'd have to do is come up with that forcing function, but that would be a function of time, and that would be the force. And so you can see that this is a very simple system that you could model as a mass spring damper, fixed base support with some kind of harmonic forcing that comes from knowing something about the mass and the eccentricity, right? This is the example I mentioned. Seismic sensor or accelerometers again fall under this class of systems. Note this is a case here that surrounds spring and damper, and note these actually are in parallel. They have the same velocity applied because the mass is moving relative to the case, and the case itself is being excited by ground motion. And so this is a seismic sensor, and depending on how it's designed, it could either be used to measure vibration, obviously vibration, but actually it could be used to measure either velocity or acceleration or displacement. So look in the reference that I've put on the course log by Thompson. He may have some discussion on that there. Finally, here's another use of the base-excited system to model, as I mentioned before, like a suspension for, it could be a vehicle, or actually it could be any kind of, even a profilometer. You might have something moving along the ground and you're maybe measuring position. And so you've got, again, stiffness damper element in parallel. These guys are moving relative to the ground, and the mass is moving right on top of these. So when you model this, you can use a basic sided mass spring damper system model. The slight complexity here is to show how, as this is moving across, right, because this is mass is moving over the surface, you'd have to figure out how to model that input velocity. That's all part of building that input function that would define how fast the bottom, this base is moving up and down. Okay, so now let's look at the model for the fixed base mass spring damper system. That's the fixed base configuration. And this, I'm assuming this is a pretty well-known model to you. I mean, something that you've seen, like I said, in physics classes and dynamics and so on. So I'm just reviewing the derivation of that using Newton's law. Usually you apply, right? You apply a free body diagram here, and mass times acceleration is the sum of the forces. So you've got your damping force, stiffness force, and then your applied force. So at the end of the day, right, you get this very familiar second order linear differential equation, right? And it's linear because we've assumed linear damping and linear stiffness, and the force here is an input. What I want to convince you to do is to get in the habit of putting this into standard form, right? So you just divide here by the term on the x double dot term here, and it allows you to define the second coefficient, which is the parameters in front of the x dot term, as 2 zeta omega n. That's by definition. And then the term in front of the x term, the term that's not going to have a derivative, is always going to be your omega n squared, right? So that whatever parameters you have thrown into here is always going to be equal to omega n squared. So omega n is the square root of k over m for this very conventional model. But any system that you model that comes out linear second order ODE, whether it's mixed, fluid mechanical system, electromechanical system, etc., it's very convenient if it's linear for you to put it into this form, because then you can recognize, what is the damping ratio? Because once you have omega n in terms of these parameters, then you can jump over here and you can find what zeta is in terms of the physical parameters, and that's why this standard form is very helpful. We also typically will make the input, here we also divide by m, so you can see actually it should have the same units, right, as the x double dot term. So this is displacement, that's acceleration. So the input is acceleration. You see, okay, hey, yes, u is f over m. So again, all that, just whenever you're writing your equation in this form, make sure you have units, consistency, and everything's correct, and so on. And then you can just define your omega n. Oh, that's here. Zeta, oh, I pulled that out of here. And note also that when you have omega n, then you also know what the natural period is. And note, this is undamped natural frequency, and this is the undamped natural period. And in a little while we're going to talk about the damped period, and it's important to keep track of all these because they're distinct, and especially when you start measuring things in the lab. Okay, so again, here's your standard second order ODE, and it's hopefully similar to something that you've seen in your systems class. Now, before we move on and look at other cases, it's very helpful to think about the undamped case. Let's throw away all the damping. See, I've redrawn it here and erased the damper from here. And so now I just have a mass spring system, and this is the very simple case. The ODE is right here, right? There's no x dot term. So we sometimes refer to this as a nice little linear oscillator. You still define that term right here as omega n squared. So whatever, again, physical parameters you have in here, that's going to define your natural frequency, your undamped natural frequency. The nice thing about this equation is it's got a really nice solution. And oh, sorry, no, it's also I'm looking at the unforced case here. So I made f equal to 0. So this is the solution for the unforced case with initial conditions. And so you see if x naught is some initial displacement, so let's say I deflect this with some value and release it, then this is this. If x dot 0 is 0, then my solution is just a cosine. I'll show you that in a second. So you need to know two initial conditions, right? Second order ODE, so you need to have two initial conditions. If this is a mechanical system of this sort, then x naught is a displacement, x dot 0 obviously is initial velocity, right? So again, this is useful because you can apply it to a lot of systems that might have this model equation that's a simple oscillator. Define the natural frequency, and I'll show you some examples shortly. And then you know a lot. It's also this is the case not only for it's very rare to have no damping, but you could have very, very small damping, and you need to verify that your zeta is very close to 0, and then you can simply apply this equation, right? And so here's what that looks like, and I refer to this as this is undamped harmonic motion because it's a single frequency motion, right? Harmonic. So let's say you were to take this little mass spring system and you displace it, right, and let it go, then the solution tells you that there's no x dot term here, right? It's 0, so it's just a cosine. So you get a nice cosine function. And if you know, in this case, K and M, your stiffness and mass, you know what that frequency is going to be. You know what that period is going to be. Or flip it around. If you don't know K or M, you have a system, you deflect it, you measure this period, and that gives you a measure of the natural frequency. And that's, for physical experiments, that's what I'm trying to get you to do, is to recognize that, hey, if I can model this as a second order, using a second order ODE, I can use what I understand about the response to design really simple experiments in the lab and extract the parameters from dynamic experiments like this way. The other nice thing about this experiment is if you release it with a known deflection this way, then it's easy to estimate other variables. So if this is the displacement, because that's the solution of the ODE, simple derivatives, right, give you peak velocity and peak acceleration, right? So this term here, just by differentiating this, so that means if I deflect it with a known value, I can predict what the peak velocity is going to be, what the peak acceleration is going to be, because I will know what the natural frequency is, right? Again, turn it around. If I measure the acceleration, right, measure the peak acceleration, I can go backwards and measure peak displacement, right? So these are very useful little vibration relationships, the most simple ones, actually, that you can use sort of and keep in your toolbox, and it's things that are easy to remember and to apply in the lab, right? You'll notice that I've left out the gravity, and what happens is if you have linear vibration systems, at least for those cases, the only thing that gravity is going to do is put the system at a different equilibrium, right? It'll make the mass compress the spring, but if you have a linear spring, you have linear damping, all that's doing is changing the point about which something might vibrate. The effect of gravity and that equilibrium becomes especially important if those springs aren't linear, and then you have to worry about how where you operate, and that the fact that the stiffness varies in a nonlinear manner. So these linear relations that we've been talking about won't necessarily hold, right? Gravity, when I talk about accelerometers in a related lecture, we'll talk a little bit about the influence of gravity and the role that plays in the basic accelerometers. All right. So the bottom line is, if the system's linear, use gravity to find where the system sits, so to speak, what the equilibrium is, and then all these linear relations hold about that point. Again, if you're not linear, then you need to follow other approaches, maybe use simulation as an alternative. Okay, so now let's consider the damped cases. Again, I'm assuming that you've seen this in other courses in physics and your circuits class. These second order systems are familiar. You always study this, right? These are second order ODE. Okay, the solutions are classified by the damping ratio, and you recall that, oh, if I find, and as I showed you, you put your model into the standard form, you solve for that zeta. That tells you what kind of solution you're going to have, right? If zeta is less than 1, we call that underdamped. If zeta is 0, obviously it's undamped. If it's greater than 0, that's the overdamped case. When zeta is equal to 1, that's critically damped. In each of these cases, the undamped, which we've already shown, underdamped, overdamped, and critically damped, all have different solutions for this simple linear ODE with constant coefficients, right? I'm not going to go through those derivations. Again, this is something that typically you will review in system dynamics or vibrations class, circuits class. And as I mentioned, some of the excerpts of chapters I put from books put in the course log, you can find some of those derivations if it troubles you not to have them in front of you. We're just going to look at the application really of just the one case of the underdamped case. Because that's going to be the system that we study in lab. So for the underdamped case, right, zeta less than 1, and this is again the unforced case. We're looking at just the response to initial conditions, right? I'm giving the mass, displacement, I'm deflecting the spring, for example. So I've got an x naught. And then I'm also allowing to give initial velocity. It's a little bit harder to specify if you think about it, to know exactly what the initial velocity would be. So a lot of times we'll say we release it from rest and then this guy is 0. But the solution, right, the exact solution is known. By the way, I say here, this is the solution here, x for zeta values between 0 and 1. Actually, it includes 0, because if you were to make this value x naught 0 equal to 0, and zeta equal to 0, this defaults to the undamped case that we've looked at already. So this should include 0. And so note you have in front of the whole this sine and cosine, you have this what you recognize as this decaying exponential with time, and it depends on zeta and omega. And that's why we put so much emphasis on finding these values, because once we find them, then we know everything we need to know about the system. Give it initial conditions, and now you've got the solution. You don't have to run a simulation. And if you have these values well defined for your system, you don't have to run experiments. I mean, that's the whole point. Of course, we'll run experiments in the lab just to verify or to show how well can we find these, how well can we specify them. The other important parameter is that now in the underdamped case, we're defining a new natural frequency, and this is the damped natural frequency. And look how it's related to the undamped natural frequency. It's related through this zeta, 1 minus zeta squared term. So if zeta goes to 0, oh yeah, so that's just an undamped case. But zeta then is obviously making your frequency smaller, right, for the underdamped case. And this also defines the damped period here. So make note of those two terms. And recognize that when you go into the lab and you've got an underdamped system, these are the parameters that you can measure. You can measure the damped period from a signal, say from an accelerometer, right? You can't measure the natural frequency, and we'll talk about that shortly. I can show you a real simple little VI I put together in LabVIEW. So all I did was put that solution in here into a little, this is a math script node, and I put in how many cycles I want to look at, but I can put in the natural frequency, zeta, and initial conditions, and in a little math script, just calculate x here and plot out x over t. And it's really just for purposes of illustration. So you can see, well, here, look, here's, it's running now, right, with my damping is 0. So zeta is 0. It's indicated here. Natural frequency is 1 for these values I've put in here of omega n equals, well, actually, I'm specifying those values and specifying zeta, right? So, you know, then you can play with zeta. You can see as I increase the damping, you can see that as I get closer to 1, I get very little. This is called overshoot here, right? I'm releasing it with an initial condition of 1, no initial velocity, and the system's coming back to 0, to the equilibrium. And there's actually a value I want to show you here, value of about 0.707. It's hard to get here, but sometimes that's, there it is, close. 0.707 is a special value. It's the value of damping sometimes used for design of a system like this. It gives you the minimal overshoot and no oscillations. You see that? Once you, and also it's the fastest kind of time to get to that value. Once you go above that, it's a little slower, right? You get less overshoot, and finally you're almost over damped. And actually, if it's less than 0.707, you can get there faster, but then you've got oscillation. So that's why 0.707 is kind of a special value. And of course, you vary natural frequency here. You can see the influence of that. My time scale is changing, so it doesn't look like it's changing, right? So that just shows you sort of the undamped solution. And again, keep in mind that the damped natural frequency important parameter that we actually can measure, and it's dependent on both the natural frequency and the damping ratio. So we need to figure out a way of measuring these, and that's what we'll talk about shortly. So now let's look at this couple of different lab models that we will consider in the labs that we run. And what we want to do in the lab is set up a mass spring damper system that's, you know, gives consistent results. You know, sometimes we've tried just hanging a spring from a mass, but that's, you know, you want to constrain it because you want it to follow the model that you are defining. So using sort of beam type springs with masses are nice because they you know, they don't oscillate in multiple directions, a little bit easier to control. So we've actually used the beam before that you have used for, say, the strain gauge by just putting a mass, and actually sometimes the mass here that we attach is an accelerometer. So we have a mass spring system. And then the stiffness is relatively easy to calculate, right, for that beam, and we've done that for that experiment. But we're actually introducing another one here is using this flex guide design that we've talked about. So here's, you know, just one story of that, and this is again also nice because it's constrained to move in one direction, and also you can show that the stiffness of these flexes can be calculated similar to a cantilever beam, but you have to take into account the number of these you have. So that's n there. So for the system we have, actually each story has 4, so you'd put a 4 in here, and then you could estimate the stiffness if you knew your Young's modulus, the length, and your area moment of inertia, right? And this is again a nice system because it's relatively easy to build. As you'll see in the lab, you can put multiple stories, and that's kind of what we'll do in the second week, is to look at, we'll go from a single story to a 2-story system, having multiple degrees of freedom. So what are some things that we try to do in this lab? Well, again, we're trying to illustrate measurement. So we're going to be using an accelerometer, but also take an opportunity to say, oh, look, we have that model. You know, let's try to see how well we can estimate the parameters that we need for that model, mass and stiffness for the components, given geometry, given material parameters. Usually that's pretty straightforward process. There's usually some uncertainty, but you can then verify or improve those once you get into the lab. And you can try to understand, where might my equations say for stiffness or my estimates of mass, where are those off? And that's something that we're trying to do with this lab, is to show you. And remember, the value of that might be is if you're ever designing, some kind of system where you're having to take into account its resonance and you're trying to make decisions on mass and structural design. You can see here how well some of these basic equations might work for predicting what those resonances might be. Damping is something that's very hard to estimate theoretically. A lot of times you're going to have to go into the lab, and that's what we're going to do. We're going to have to measure the system motion to basically extract damping ratio, and then from that we can estimate the B value, and I'm going to talk about that shortly. So that's one of the other things that you're going to be doing in the lab. And then also, even though we can theoretically estimate undamped natural frequency, damped natural frequency we can't. So these kind of go hand in hand, but we're going to look at what it takes to estimate those values. And once you get into the lab, of course, we want to see how well those system parameters can be estimated, and also once you have them, how good is that model in predicting the actual measured response? So we can compare the theoretical predictions to the measured response. And keep in mind, since we're measuring acceleration, you're going to be comparing acceleration. So remember, the solution for this mass spring damper system was for the displacement. So for the damped case, you're going to have to differentiate that solution twice to get acceleration, so you can compare those acceleration to the measured acceleration, right? Or you might think that you can take your accelerometer measurement and try to estimate displacement from that, since that's the solution you have. That's another little challenge for you that we're going to introduce in the lab. Can you integrate the acceleration to get displacement? How well does that work? And so we'll give you an opportunity to do that as well. Okay. So let's take a look at the first few steps before I show you how to estimate some of the other parameters, the system parameters, natural frequency and damping. And I'm just trying to show you, when designing this experiment, just kind of sketched out the concept of this flex guide using these U channels. And what I have done is on the course log posted the actual raw materials that we bought off the MasterCar website, so you can look at the actual design and note the actual size that this came out to be is 5 by 5 here, right? And these beams are 7 inches, okay? And also there's some screws here. I mentioned that in the pre-lab. So in the pre-lab, what I want you to do on the first one is actually just estimate the mass. There's the U-channel piece here, and then there's a clamp piece on both sides that clamp this tempered steel part. The tempered steel is what's making these flex guides, and that's what you're going to need to take into consideration in estimating the stiffness using the relation I just showed on the previous slide. So I've shown you some of the parameters here. And also there's some screws here. By the way, the screw set here I gave you, it's about 5 grams each. This is aluminum for all those the mass pieces here, tempered steel for these flex elements. Okay, and I found that you might use a nominal value for aluminum, and it's going to be a little off. So once you get to the lab, you're going to have to probably update your values, but you'll come relatively close on the mass, and possibly on the stiffness too. But there can be some uncertainties, and that's kind of what I want you to explore a little bit and see where you think you might be off. Okay, so the question being, how well, given just those raw values, can you estimate the natural frequency? And so once you get into the lab, you can go in there and actually measure the mass of the structure. You can even try to measure the stiffness, displace measure force and displacement and get an estimate of your stiffnesses directly, and get a little bit better estimate of omega n, and then try to assess how accurate the value is. But another comparison that you can make is by actually measuring, right, the response. Give it an initial condition and let it oscillate. But keep in mind that you can't directly measure the natural period, which would give you the natural frequency, undamped, right? Because you always have some damping, and even though you're going to see that one of the things I didn't do well on this design was put enough damping in there, it's a pretty lightly damped system, so you're going to find that the zeta is small, but it's not zero, and it'll allow you to see, when can I assume that my zeta is small enough so that, hey, my damped period is which I can measure, right? Because it's always damped. It's actually pretty close to my natural period, and the thing to recognize here is you can measure this guy, right, from your signal, because that's in reality what you have. You're trying to find the natural frequency, so you have to measure damping, and that's what we're going to talk about shortly. How do I measure this zeta value? I'm going to show you a method for doing that. So you can only estimate omega n if you have an estimate of zeta, which can be done by using the log-decrement method. So you can see kind of the combination of methods that you have to use in order to finalize your estimates for these parameters. See, once you get an estimate for omega n, then you can compare it to your theoretical value, and you can see whether you're, how close you came to estimating, what you can actually observe in your system, because your stiffness might be different from what you expect, right? Or it might behave differently. And let's look at some reasons, actually. Before we look at the log-decrement method, I want to show you at least a couple of reasons why, your K and M values could be off. And let's look at the influence of the spring mass on undamped natural frequency, right? Normally, when we model these systems, we're making an assumption that, okay, we have this, sort of call it the main mass, and here's some bunch of little examples in this table from this book by Den Hartog that's referenced here at the end of these slides. But Den Hartog shows several simple systems and formulas for estimating the natural frequency a little bit better than if you were just to assume that, hey, I've got an ideal spring here. Remember, an ideal spring is a spring that you assume that there's no mass, but let's say that this spring here had some mass, little m here. The main mass is m, and this is a translational vibrating system. This relation here shows that when I estimate the natural frequency, I take that stiffness, take the main mass, but to the main mass I add about a third of that spring mass, right? Again, what we're doing is taking into account the fact that that mass in that spring is going to make itself known in the way the system actually vibrates. And so that's basically what is being done in each of these formulas, right? Even for this rotational system, you've got the rotational, actually this is this is mass, this is rotational inertia, right? And then there's a stiffness in that rotational, torsional shaft. And then here's the main rotational inertia. So very similar to actually the translational case. And then here's some other cases. The one that we've actually, because we've studied the cantilevered beam with a mass at the end, so look at this one, we would try to find if adding 0.23 times the beam mass would give us a better estimate of natural frequency than if we were to just ignore this mass. Right? Now these values that Den Hartog shows here, they're not experimentally determined, they're actually theoretically determined using a method, which is kind of like an energy method called Rady's method, and it's described in this handout, this is actually a chapter from Thompson's book, for any of you that are interested. So again, given the mass of the actual element, you could add that, and that might give you a better estimate of your natural frequency. That's one possible source for why, when you go and estimate your natural frequency, assuming ideal stiffness, ideal mass, you go into the lab, eventually get out an estimated natural frequency. If there's a difference, one reason might be, that you didn't account for mass in the spring. The other reason might be that the stiffness might be off. So one way that you could approach this, let's say before you walk into lab, so that you feel a little bit more informed, is to maybe put some bounds on your undamped natural frequency estimate. In other words, don't focus so much on one value, because there's always going to be some uncertainty, right? So the influence of the spring mass suggests, maybe what you want to do is look at the range that you should expect. And here's just one example. Say you consider the case where the spring is massless, right? Which is the way we normally approach it. Then we can get one estimate of natural frequency. The alternative is to say that whatever spring I have, I'm going to take its full mass, add that to the main mass, and now I'm going to get another estimate of natural frequency. Right? This natural frequency is going to be lower than this one. So when I think of the bounds, actually, this one is much lower than this one, and so that natural frequency is less than that one, and in between is the actual, right? So I hope that my natural frequency, this tells you, at least walking into the lab, what range of frequencies you have. Think about how useful that can be. You already then know, what is the frequency content of your signals? How fast should I sample so I can collect signal? All of that information that's typically useful when you're going to go and make measurements comes out of making some simple estimates like this. Of course, we are just uncertain about what the mass might be. There might also be some uncertainty in the stiffness, right? So you could actually do a whole uncertainty analysis on this basic relation and find more accurate bounds on your natural frequency given whatever uncertainty you think you might have in the stiffness and the mass. I'm just trying to show you one way to estimate those bounds. Okay, so I think instead of doing an uncertainty analysis, you might think, hey, if I can estimate one really well, I'll get my bounds based on the one that I don't. And that's just the example I'm showing here. Think about which one of these, is it stiffness or mass, that you think you're less certain about on this one case, and then create some bounds and see how well that your actual one comes between those bounds. Good practice calculation, I think. Finally, one last thing. As we saw, in order to determine the natural frequency using the measured damped natural frequency, we need to measure the damping ratio directly. So one way to do that is with this method that I'll show that's called the log-decrement method. The thing to keep in mind is with damping, unlike with a spring, for example, the only way to measure damping is dynamically. With a spring, right, you can hang the spring statically and put forces, statically measure deflection, and you can come up with a stiffness. With damping, you have to have motion, right, because the force of a damper only makes itself known when you've got relative velocity of its ends. If this damper is just sitting still there's no way for you to assess what its damping characteristics are, right? And so what we do is we refer to the model. So from the model for the underdamped response, right, and I'm just reminding you of that equation here, just rewriting it here to show you that this looks like kind of a damped cosine, but with some phase here. Don't be so concerned about that. The main point is this amplitude is a constant, right? This A naught, which if you do all of the if you rederive this in terms of the cosine with phase, the A naught is constant. It depends on the initial conditions, and it's a damped exponential, right? So that's a very useful thing. We end up not really caring about the phase for what we're going to do next. So the important result here is that the amplitude of the response follows this decaying exponential, which is something that's useful to us, right? So what we can do then is look at now at just the peaks, kind of like the way we did with in an earlier experiment with the pendulum, right? You can just look at the peaks and you could discern something about dissipation, you recall. Now we're looking at this amplitude decay, and by using the analytical solution, we can see that the ratio between two cycles, between two peaks, let's say n is the number of one peak, and then the next one is a sub n plus 1. you can show that that ratio is simply the exponential zeta omega n and the time between those. Now, the thing to note is that this time difference is something that we can measure, right? This is also something that we can measure. So the period between those peaks, this difference here turns out to be the damped natural period, right? And remember, that's related to the damped natural frequency, which is this expression here, right? Omega n 1 minus zeta squared. So see, it depends on zeta, right? That's a nice result. So if you now take the log of both sides of this equation, having replaced this time difference with this relation, right, then everything turns out, seems like to be a linear relation. The natural log of the amplitude ratios, right, is some constant. Look at this, it only depends on damping ratio times the cycle number, right? So if you plot the log of the amplitude ratio as a function of cycle number, the slope gives you zeta, right? Stated here, this shows that the log of the amplitude ratios, what we call the log decrement, is linearly related to the cycle number by a factor that's simply a function of zeta, okay? So here's what some example decays would look like. Just say if you were just looking at plots of these. Actually, the one on the right here should look familiar. Actually, this is pendulum data. And you recall that pendulum had damping that was not linear, and it had linear decay. So the nonlinear friction gave us a linear decay. That was kind of a unique aspect of that. But when the system has linear damping, you actually get an exponential decay, right? That's what that model says. So this shows you that without even doing any analysis on the data, if you plot response, say you just deflect the system, let it go, and you see an exponential decay, that should tell you that the system is probably linear. If you get a linear decay, it's dominantly nonlinear, right? Now we don't know, we want to quantify this, and in order to quantify that, we have to do a little bit more work, but at least again, from just insight and from observation, this is a good lesson to take away here, right? Exponential decay, dominantly linear. Linear decay, dominantly nonlinear, okay? So when you plot, now let's quantify this. When you plot that log decrement as a function of n, this now quantifies what we just said. The linear case is going to have a nice linear relationship between the log decrement and the cycle number, whereas that linear decay, actually you get a non-linear relationship between log decrement. So this one you would say, oh, I cannot model this system with linear damping, right? Whereas this one, if you have this straight line, I can model this with linear damping. And this slope here is related to zeta. It's not zeta, it's actually beta. And so you take the number from here, that's beta, and then you could solve this simple quadratic equation for zeta, okay? You could do this a lot of ways. You could collect your signal, drop that signal into Excel, and do all this analysis. Let me show you another way to do that. Here's a little VI, and I've actually given this to you. And it has a sub-VI under here. And I'm going to actually show you the block diagram, but I'm not going to show you the code that generates this because I want you to rebuild this. I want you to take the one I've posted this VI here without the code for just so that you practice with that analytical solution. But look at what this, let me explain what this VI does. You give it an initial condition, you give it a zeta value, you give it initial position, initial velocity, which usually will release this from 0, so I'm making that 0. You give it some time parameters. It's not running a simulation, it's actually just computing the amplitude, the deflection from the analytical solution, right? So you're going to just use that formula. So you don't need to run a simulation. Give it a mass, and these could be the masses of your system, right? So whatever mass you estimate, you put the stiffness in here, you put the mass, give it a zeta value. And what it does underneath is it calculates what that B is. But then what it also does is it illustrates the use of this little VI that I've given you, which what that VI does is it takes this decaying signal and it picks off those peaks. I'm going to give it a little bit larger initial condition so you can see what it's doing. The red points indicate that it's found those peaks. What it does then is it shoves that signal into a little VI. That VI actually finds those peaks, takes the amplitude ratio of those, plots it versus cycle number, and generates this graph, right? And then what it does is does a linear regression on that, finds that slope, solves the quadratic, and pumps out zeta. So over here, I've put in a zeta of 0.01, and my log decrement VI is giving me 0.01. On a real signal, expect that, this can depend on number of points you've collected. It could also, if there's noise here, this is a nice perfect signal. So you can get some, noise in this graph too. So, but check this out. When I run this continuously, let's drop this maybe to, say 0.5. So you can see a lot more oscillation and see it perfectly finds zeta. Again, when this is, you might do that when you build your little simulation VI, which is part of the pre-lab. Just put some noise in there and see what it does to your estimation of zeta if you like. You don't have to, but that'll happen when you use the same VI. Practice with it here for the analytical solution, but then you'll use it when you go to lab. Let's stop this. And that is all. So discuss some mass spring damper system models to provide insight into how these can be used to understand how many practical vibration problems are studied using those models. These are models that also can be used to understand accelerometers. In lab, we're going to use an accelerometer to measure acceleration, and I'll talk about that in a short related lecture video. And when you estimate your parameters for your system this first week, those are going to be used in a second week to study the full two-story system, and we'll talk about that in an upcoming lecture.